non-observable states and non-controllable states. So we consider this system, which is a state representation of a four-dimensional system with a lot of ones and minus one in order to facilitate the computation. So the first question is we have to compute the transfer function. So this system is given here. And we have the matrices A, control matrix B, observation matrix C, and here the direct matrix. So of course this system has one input U and one output Y, so we can compute a transfer function. So the formula tells that J of S is equal to C times Si minus A inverse B plus D. It's not so easy to compute by hand. That's why I prefer to use symbolic calculus for this. And I propose to use SymP for this in Python with the following program. I have my matrix A here, so SymP, I use SymP, and the symbol that will be used is S for the Laplace variable. So I define my matrices A, B, C. I print them just to check that I made no errors. Then I compute with this formula J, and I simplify it just to have some consolation. Otherwise, SymP will not spend time to make some very elementary simplification. And then I print the transfer function J. This is the program. I run it, and I can see here my matrices A, B, C, and the transfer function is S plus 2, S plus 1. So this one is equal to S plus 2 divided by S plus 1. So in this case, it means that normally the transfer function has should be normally of on the denominator the polynomial should be of dimension 4 because it is a 4-order system. What happened here is that we had some simplification for such. For instance, assume I could have something like this, s plus 1, s plus 1 square, and the simplification of the square with this one gave this. It is what happened, and I will see why it may lead to some problem. Now, another way to compute the transfer function by hand is the following. I take this equation, the state equation, and I will compute directly the Laplace transform, and I will try to express y hat with respect to u. So I have from this equation, I can see that y hat is equal to x hat 1 plus x hat 2 plus u hat. Now, due to this equation, I need Sx hat 1 is equal to minus x hat 1 due to this plus x hat 2 due to this plus u hat. I also need x hat 2, so x2 equal to, due to this, x hat 2 and nothing for you. So here I can see that this implies that x hat 2 equal to 0. So now this simplify here, and I get that y, which is equal to x hat 2 plus u hat, it will be equal, due to this, to 1 divided by s plus 1 plus 1 times u. So it means that the transfer function is j of s equal, so if I reduce to the same denominator, I will obtain s plus 2 divided by s plus 1, which is exactly what I have computed with Python. So we can see that in here I had no link between y and u. Question number 2, is this system stable? I have two possibilities to check that the system is stable. I can have a look to the transfer function and to see the denominator, or also to have a look to the eigenvalues of the matrix A. But here, since I had some simplification, we'll see that the characteristic polynomial of the transfer function is not the same as that of the matrix A. So I take the matrix A, and if I compute the characteristic polynomial, I will get P of S is equal to S4 minus 2S3 plus 2S minus 1. And the roots are minus 1, 1, 1, 1, so 1 with a multiply 3. So how can I compute this? The possibilities to use also SIMP and to add is 3 lines. So I have my matrix A, I compute the eigenvalues, I compute also the characteristic polynomial, and I will print. So here is not A, I will print P. I switch here, so P equal, I run the program, and I obtain the eigenvalues here, 1 with a multiplicity 3, and minus 1 with a multiplicity 1. And the characteristic polynomial here is given in a factor form due to this, and we can see that, of course, I can recognize the eigenvalues, so 1 and minus 1. So what happened is that in the transfer function, the poles are equal to s equal minus 1, which is on the left part of the complex plane, which corresponds also to this, and which is stable. But these poles are unstable. They are on the right of the complex plane, but they have been simplified. And in practice, even if the input-output behavior is represented totally by this, we have to recall that the linear system is an approximation of the real nonlinear system, and the approximation has been done by linearization. So if one of the state variable is unstable, of course the approximation will not be correct. This is why this kind of simplification by unstable pole are not have to be avoided. Equation number 3, I have to draw the circuit associated to this system and to have a better understanding of non-observable or non-controllable states. My system is here and I will try to draw the corresponding circuit. I draw my 4 integrators, one for x1, for x2, for x3, and x4. If I take x1, I can see that I can reach from U a plus here, I plus everywhere, and here I have x dot 1, x dot 2, x dot 3, x dot 4. From U I can reach x1 and I can reach x3. Okay. Now for x dot 1, here it's minus x1, so I have something like this, minus 1 plus, and here from x2 I can reach x dot 1. Here for x2 I have this, for x dot 3 all states are here can reach plus, so here I will put a plus this one. I will have also this one and x4. Okay, now for x dot 4 I have x2 and x4, so x4 and x2, so x2 here, okay. And now for y I will have the sum of x1 and of x2. I have also u. So to study the transfer from u to y, I am interested by all paths that start from u and go up to y. I can understand that if I am in x3, uh, I uh, I cannot reach y. There is no path to go from x3 to y. So it means that x3 x3 is said to be non-observable. But since you can reach x3, you can influence the state and it will be controllable. Now, what about x1? I can see that x1, from u I can reach x1, and from x1 I can reach y. So this one is said to be controllable and observable. x2. x2 can reach y, so it will be observable. But from u, I cannot reach x2, so it will be non-controllable. And now x4, from u, I cannot reach x4, so it will be non-controllable, but from x4, I cannot reach y, so non-observable. So there is some simplification, since indeed from x3 I cannot reach y, there is no influence on the input-output behavior, and this can be removed. Okay. Now, if I am now this one, there is no possibility to go from x4 to y, so I can remove it. About x2, if I am here from u, I cannot reach this one, so I will remove it. And at the end, I have only x1, and if I take this system, then if I compute the transfer function of this system, I will obtain g of s is equal to s plus 2 divided by s plus 1, as I have previously computed. The last question. The pole of the system are composed of transmission pole and hidden pole. I have to give the hidden modes. So the hidden modes are those that have disappeared, and it is clear that the transmission pole corresponds to -1, which is stable, and now the hidden pole or hidden modes are all unstable and correspond to 1, 1, and 1.